Welcome to lecture. Discussion on the generalized gradient descent and look at its accelerated version, specific versions like proximal gradient descent and projected gradient descent. So I had given you some food for thought. Application of the so-called generalized gradient descent. The homework was applying this to the lasso problem, right? For which we were trying to kind of complete our evolution of the ISTA algorithm. It's iterative soft thresholding algorithm. Okay, so we call that the whole idea in generalized subgradient or generalized gradient descent is that you have this function fx that you're trying to minimize, capital Fx, which is a combination of a differentiable function fx and a non-differentiable function cx. Okay, so we'll be using cx or hx interchangeably. I've deliberately used cx for the following reasons. So we'll do later use hx for proximal. Recall in the last class I said that the C could also be encoding indicator functions on constraints. That's why C is sounding like constraint also. But very often it's not denoting any constraints, right? So in which case we where hx won't denote constraints. But just say non-differentiable function. Such as Px. Such as the one in which case we'll just use hx. Cx is therefore, as I said, for a particular purpose. Okay. With this note, what we did in the last class said, well, we could try and have a first order approximation for fx, leaving around xt and leave the cx part as it is. Okay, so that first order approximation was only for the fx part. That's exactly what corresponds to the gradient descent iteration. So what does gradient descent do? It minimizes this approximation exactly. And how does it do it? It says, well, plus 1 xt minus gamma times the grade of it. So we can verify that. But now what we have done is we said, oh, we're going to use the first order approximation for fx. And we're going to leave cx as it is. Okay, so what does that lead to? We also said that this basically can be reformulated as the first component rewritten as a squared difference. Exactly the same. So squared difference between the gradient descent iterate and the new point x. If this was only component, the new point x would be exactly the gradient descent which we had in the previous slide. So just copy this part again. So what we're trying to say is that so gradient descent minimizes this exactly, right? So this proximal is coming for a particular reason. What's the reason we call it proximal? It's because I'm trying to get the proximity to a gradient descent iterate through this first order approximation slapped with the CS. That's why it's given the name proximal. Okay. So with this note, I had left you with a homework problem where you had to recap what happened with lasso. Lasso, I mean, we didn't actually solve lasso. We just said, okay, simplified version of lasso. I mean, we said this is like a simplified version. Had kept it abstractly at that point, right? So, what was the solution here? Did you try and recap? Yes. So, what we have done is we have instead of 5x minus y, we have z minus x minus z. That's it, right? So think of this pi as an identity. So you can set this z, right? So here, this component z you set to xt minus gamma times gradient of f xt. So you just set this part. So what is this implying? It's basically saying that I will take a gradient descent step for this part. So let's write it in plain English. Plain English. Step 1 to a gradient descent for this component. Right? Let's write down the gradient step. What's the gradient step going to look like? Xt plus 1 is xt minus. Now we want exact step. Gamma. What's the gradient of this component at t? Yes. I hope you're able to hear me. Yes, I'll xt. 2 into 2 into. Okay. Will there be a phi transpose also there? After that? Tell me the exact expression, please. I hope people on the call are able to hear me. Just please confirm once more.
Yes, sir.
Hello?
Yes, sir. We can hear.
Ishaq, can you confirm that you're able to hear me?
Yes, sir. We can hear you.
I'm muted. I can't speak. What's happening? Yeah, can you hear me? Okay, we can. So minus 2 gamma phi transpose phi xt minus phi transpose phi. Phi is a vector of all the predictions. Is this correct? So this is an exact expression. You set it this way, and then what will you do? Step 2. Setting z equals exactly this xt plus 1. Solve for the prox operator, which is prox gamma z is argument over x of 1 upon 2 gamma x minus z, which is exactly x minus xt plus 1 plus lambda times the 1 norm of x. So I'm bringing the regularization post facto. So bringing the regularization up front, I'm saying let me solve the gradient step and then bring in regularization. Is that clear? This has come in post facto. That's it. That's exactly the application of the generalized gradient descent now to lasso. That was our kind of homework settings, right? Did anyone derive the steps? Let's derive the entire actual steps. So what would that be? Anyone? It was in terms of lambda. I think 1 upon gamma, we had to factor into lambda somewhere. I put it's the same basically as saying r1 over x of 1 upon 2 x minus n norm square plus lambda gamma 1 norm of x. It's the same. I just multiplied the whole thing by gamma. Okay, so what would be the exact solution now? So remember we had this soft thresholding operator. We'll have to bring that in. This was solved, right? This was recap from what are we recapping? Sufficient condition based on setting the subgradient to 0. It is a subgradient to 0 rather, right? Okay, and that was basically what. So with just 3 conditions. So we're saying that prox, the ith component of prox z, right? So what was yi minus, that will be yi minus lambda gamma, right? Sorry, if yi greater than lambda. And what is the role of z? You didn't, you're not doing anything with z. It is just yi or something else. How can it be just yi? What's the role that? Yeah, so we have to bring in. So this y. I mean, this y is our z, right? So we have to write it in terms of z. Correct? It cannot be y. Z. If zi is lambda 1. So it's very simple. If it's high, threshold it, bring it. And 0 if zi is between minus lambda gamma and plus lambda gamma, and zi plus lambda gamma if zi is less than equal to minus lambda. Is that correct? Is that what I wanted you to attempt as homework? Okay. Okay, so just let me just now outline the entire iterative soft thresholding algorithm for solving lasso, all under one umbrella. Okay, so we have phi w minus. Okay, now I use w instead of x. That should be okay. This is the x, right? And exactly using what we call proximal subgradient descent algorithm, where to error EW we have also added a lambda w or lambda 1 norm of w. So wt plus 1 is the next gradient iterate for wt. Compute wt plus 1, which is argmin over w1 upon 2 gamma, blah blah blah, by setting a subgradient. I mean, if you want to be more specific, you can say by setting a subgradient or some subgradient. Right, and this is exactly what I derived on the last slide. Okay, but now to be more specific, this will result in w, which is or wi, which is wi t plus 1 hat, or if you want, you can call it wt plus 1 itself. Let's just call it wt plus 1. Wt plus 1 I, which is w hat t plus 1, which is without the non-differentiable component, minus lambda gamma, lambda gamma sorry. I keep putting an I index everywhere. Okay, this is the overall algorithm. I think I've written this. I'll just recap this from lecture 13 exactly. It will be based on the soft thresholding operator. This we call the soft thresholding operator. Okay, so now so that's it. Oh, did I have by2? I think this by2 is wrong. Should this be? Wait a second. It should have been probably. By2 is wrong. Huh? It should just be. Yeah. It should not be by 2. It's not by 2, right? I mean, just confirm. Remove those by 2. Okay.
What's a very different
That's a good point. What will be a good stopping criterion? What did we use in our collab notebook? Difference is less than epsilon. We also use the 1 norm or infinity norm. Infinity norm of the W at the largest component of W is not too big. A different stopping criteria. Okay, so we have left it open. Could be either of 1, the infinity norm, which is to check if the max component W is small. Okay, so that's one. We'll also look at difference between the function values. Function value, absolute value is very less, or that's difficult to check because we don't know the optimal value, but function has decreased sufficiently. Or difference of weights or difference of function values. Typically, you should do difference of function values.
For smooth function,
Smooth functions it won't matter. Okay. Okay, so now let's discuss some other cases. I think we're done with the application of proximal to lasso. What happens if Cx is 0? You can basically get gradient descent, right? I mean, gradient descent, or you can say, or subgradient descent. But if you have an indicator function, the second case, where you have a constraint, or maybe a bunch of constraints as shown in the last class, C1, C2, right? And each of them has an indicator function, IC1, x is 0 if x is in C1, and let's say infinity otherwise, right? Likewise, IC2 requires that x is in C2. Okay, so if you have some indicator functions like these, to insist that your point lies in the center region, you get projected gradient descent. Proximal minimization is another check where you are trying to find a feasible point x. You're not even trying to minimize a function. Fx itself is 0. You don't care to minimize, you're trying to find a feasible point. I have a bunch of constraints and I want to check if I'm able to satisfy those constraints, for example. Or I just have a non-differentiable function, no differentiable components. That's proximal minimization. That's a special case. So, no differentiable component at all. Projected gradient descent, we'll just see quickly. But let's understand how well we are doing on convergence. Right now, let me ask you a question. So coming to convergence, how was the convergence of subgradient descent? See, we could have applied subgradient descent on this overall non-differentiable, right? Function. Cx is non-differentiable. So how was the convergence of subgradient descent? Can you recall? Omega 1 upon. Okay. Or in terms epsilon was diminishing like 1 upon square root t, right? 1 upon square root t. That's how it was. The error was decreasing. Epsilon square is time. Omega epsilon 1 upon epsilon square is a time, or omega 1 upon square root t is the error. Right. So if we apply subgradient descent to fx plus cx, we could do omega 1 upon, we would omega 1 upon epsilon square, as you said. Sorry? No, omega. Huh. So if you bring it to the other side, it'll be the same. Right? Okay. So you could do it in so much time. Or error would decrease as omega 1 upon. This is exactly what I wrote above. Okay, but are we doing better? I mean, if you're not doing better, might as well go back to subgradient descent. And we were not very happy at all with subgradient descent then. But yeah, there is a reason why we call this generalized gradient descent. What do you think? Should behave like subgradient descent or like gradient descent? Huh? You think it will behave like subgradient descent? It should encompass both the classes, yes. See, but there is some, now we are trying to be smart, right? We are trying to do proper gradient descent on the first component and use the Cx as an afterthought. Yeah. And in fact, I'll show you examples. We are minimizing, but since generalized gradient descent avails, right? So let me make that point. So generalized gradient descent avails of the regular gradient descent. Update and brings Cx as an afterthought, almost like an. For this, can we expect it to behave like gradient descent or avail the advantage of gradient descent? So what's the convergence of gradient descent? Obviously, we can't expect strong convexity overall. Or rather, can we expect strong convexity? We can. Huh? If you are L2 now, but not otherwise. So at least the advantage of gradient descent. How many we have to see? For example, under Lipschitz smoothness, we could do something better. So can I say it should be at least, omega 1 upon t? Because omega 1 upon t is at least that much we should do, right? We would probably do omega of t raised to some factor, right? Or log, basically log 1 upon log t. But at least 1 upon t we should do. T square, we saw t square also we got under, I think, Lipschitz continuity. Sorry, under Lipschitz smoothness plus convexity. So let's put that as a question mark. Do we get there? Okay. So this is the analysis. If fx is convex, differentiable, and the gradient of f is Lipschitz continuous, that means f is Lipschitz smooth. So only for f we are expecting Lipschitz smoothness. And Cx is convex, which should be fine. And the prox operator can be solved exactly. That's important. In ISTA, we could solve it exactly. Right? In ISTA for lasso, we had a closed form sufficient condition. Not for the entire solution, but for the prox. Right? It was in terms of, soft thresholding. So we had in terms of the soft thresholding operator. What was that? S, whatever, lambda, gamma, lambda of Z. So if you have that, so in ISTA this qualifies. C being convex is okay, right? So e.g. norm of one norm of x cannot be differentiable, but is convex. Right? F is convex and differentiable, which is fine. Lipschitz continuity can we have for the gradient? That is pi x minus y squared. This is Lipschitz smooth, right? So under these conditions, you get exactly what we expect. That is omega 1 upon t. So you get this expression. Fxt minus fx star is less than or equal to x naught minus x star the norm square divided by 2 gamma t. Okay, I've made a small note here. Sorry. Should that be? It should be capital T. The left one, right? Yes. This one. Okay. There's a small note I made here. What happens if prox cannot be solved exactly? So else. I mean, else what you can do is you can treat that prox itself as another minimization problem. That option always exists. Right? So again, do gradient, I mean, do something else, do subgradient descent there. Right? Approximate solution, say, using no subgradient descent. But at least you're doing gradient descent for the first and then do subgradient descent as an afterthought. Okay. Okay, so for subgradient descent, now there's a contrast, right? Subgradient descent had convergence rate. Oh, sorry, this is omega. Omega.
omega. Okay, and now for generalized. We already now seen we are getting omega 1 upon t. So can you now quickly tell me where are we getting this gain? How is this really happening? Oh, sorry, that is epsilon squared. Yes, I beg your question. Okay, so where are we getting the gains from? What's really benefiting us? The fact that we are taking the full gradient step, right? Okay, so this is really good news for us in some sense. So these are the reasons. Better convergence. Okay, this I think omega everywhere. Because of assuming the following: differentiability of fx, Lipschitz continuity of gradient, which we could not do again in subgradient descent. So that's also an advantage. Now the good thing is, it's not just this. You can now avail accelerated gradient descent as well. Okay, where will you use accelerated gradient descent? Just by this decomposition of some sort. How are we not able to avail a lot more? Where can we do accelerated? Anyone? I think this is the most exciting part. Where will you do accelerated? So what could we do instead of, say, prox gamma? Right? You could have done xt minus gamma gradient of fx. So this is the gradient descent, right? But instead of this, what could you do? Use the proximal step on the accelerated step, right? Prox gamma on accelerated step. Right? So we may not have strong convexity on Cx, but we could still have strong convexity on Fx. Can that be availed? Right? So now you can think a lot more proactively. Let's take more examples. Very good question. Okay, so very good question. Can be solved exactly is where you're raising a question. As I said, if it cannot be, then you can do basically subgradient descent, right? But let's take this very seriously. I'll show that for several cases, you can actually compute prox gamma also in closed form. That's why the whole fun. Right? In several cases of non-differentiable Cx, as well as in several cases which the Cx denotes constraints, indicator functions. The prox step be not only computed in closed form but computed efficiently. And that's why we are excited about the whole thing. This is okay. This is very it's very hope giving that we are not just limited to the weakest chain through subgradient descent, but we can decouple that part through a proc step. Okay. Right. So this entire analysis assuming you got the proc step efficiently, hopefully in closed form like we did in ISTA. That's why ISTA is very fast because you can solve that in closed form. Okay. So I'm giving you proof for this kind of generalized gradient descent and its accelerated version, but it's really extra additional optional material, which I will not get into, right? So this is just going to be optional. Okay, let's now look at the more important part of when we can actually solve this in closed form. Okay, so before I get there, a quick kind of special case of projected gradient descent. As I said, the example is Cx is indicator function on Ix. Right, so you could have, for example, an indicator function which says as positivity, right? Ix is so let's say it's infinity or Ix is x if x is greater than 0 and equal to infinity otherwise. So what is what is this projected gradient descent going to do? We will talk about it a little later. But what do you think this will do? If so what will this do? I'll find xt plus 1 is xt minus gamma. It's a gradient of xt, right? And then that's what I would have done ordinarily, right? And then I'll need to do a proc step. Prox gamma xt plus 1, which minimizes basically, right? Which minimizes x minus xt plus 1 norm square plus, oh, this is gamma lambda. I think this is lambda. Anyways, I can use lambda here. Right? Plus lambda times the indicator function. This particular ICX. Sorry, you're asking a question. What should be the? Well, indicator function I talked about in the last class. I'm just saying that if you're in the set C, okay, in this case, the set C is just all the positive quadrant, right? So if you are in the set C, you're doing well. If you're not, then you're doing horribly bad. I mean, not just bad. Horribly bad means infinity. You just kind of bombards, right? So how do we do that? What will be the solution here? So this is the indicator function. What would the prox operation yield? Yeah, but lambda doesn't matter here. It doesn't matter, right? In this case, it doesn't matter. You can remove it, yes. But what will the output be for finite choices of lambda? What would that be? You would have, say, xt plus 1 I if xt plus the ith component of xt plus 1 is greater than or equal to 0. What will it be otherwise? If xt plus 1 ith component is negative, what would it do? Huh? 0. So it's basically just thresholding it. I'm saying I can't anyways exceed 0. I'll be on the border, the boundary. The boundary of the set is here, right? X is 0. This is clear? A simple example. So there are also other special cases. You set the fx to be 0, then you get something called alternating projection, proximal minimization. There are also alternating direction method of multipliers. These I'm going to give just extra additional reading. We will really not have time. Okay, but I'll talk about projected gradient. And lasso we have already seen as a special case for specific objective. Okay, just some more thought here. This omega change. And Lipschitz continuous, plain Lipschitz continuous without strong convexity can be generally very slow for convergence. Any ML problems such as L1 regularized logistic regression are Lipschitz continuous. So the main assumption that the function that causes the non-differentiability is simple, and therefore we are able to isolate it. So you can isolate it to yield the remaining part that is Lipschitz smooth / strongly convex, right? All the nice properties. Okay, so that's another reason why all this acceleration helps significantly. Not sorry, proximal helps, right? So this okay. Okay, so just recap. This is the overall step. I'm just running through it. And now the optimization problem is min over x, fx plus cx, CSC is non-differentiable. The update then basically becomes of this sort, xc plus 1. And after some manipulation, this is where we are. What is confusing? So I think for the first time that starting last class, we took this fx plus cx. So what we are looking at is min of x, fx plus cx. So far, we never had this cx component separately. Okay. So this is totally, we never had this earlier. We began with this only in lecture 19. Okay. Okay, and then the convergence bound we found is LR square by 2T. Okay, now we're going to delve a little more into how easy it is to compute the prox operator. Or rather, let us see when computing the prox operator is easy or feasible. Okay, so I'll start with very simple examples, but then these examples can be composed as well, because there is a calculus of prox functions. Like we talked about calculus of subdifferentials, calculus of convex functions. There's also calculus of prox function, prox operator. So okay. So here are some examples. If Cx is A transpose X, how would you compute the prox operator? Let's take this one example. Well, C is not even non-differentiable, right? I mean, are any of these non-differentiable? Well, log X at X is 0. What do you do with X at 0 for log X? Certainly is defined for X greater than 0. So this actually should be X greater than 0. Okay, log X is defined for X equal to 0 as well, in sense 32 minus infinity. But do you have a problem with having the derivative? So how would you compute in these simple cases? Yeah, this is very simple. So all you need to do is compute the gradient C dash, right? So the question, therefore, the more interesting thing for which we designed the whole the apparatus is non-differentiability. So what is the function is non-differentiable? Okay. So there's a slightly notational aspect here. Sometimes you define the prox operator as prox new C because you're trying to find a new estimate based on the old estimate. So you can think of this Z, which is xt plus 1 hat, or so to speak, which is xt minus gamma, whatever. So that you could use an accelerated gradient descent also. So this is basically your old X old, right? And therefore, some textbooks say is prox new, but that's more of a notational aspect. Okay, so main ideas for computing prox operator for a convex function is C dash X is 0. If C dash X is 0, then X must be one of the minimizers. If the minimizer exists and is not attained in any point of differentiability, must be at a point of non-differentiability. And that's where you look at subgradients. You look at the lower bound tangent. And that is what we did in lesson. But let's look at slightly more tricky, I would say, it is functions with points of non-differentiability here. Yeah. If it's a strictly convex function, it will have unminimized. So the question is, if it's convex function, why are we talking about one of its minimizers? Because a linear function can have multiple, in fact, count to be infinite number of minimizers. Okay, so let's consider some of these cases. Cx is lambda x cube if x is greater than or equal to 0 and minus infinity otherwise. Now this is becoming like a projection, like an indicator function. So what would be the Bloch's operator for this, the first case? Let's try and compute. Let's do the first one quickly. What would be the Bloch's operator? So it's not just lambda x cube. Huh? Scalar. X and Z, yeah, they are scalars. First case X and Z, I mean, all of these are with scalars. So what would that be? Fairly straightforward, right? I already gave you the example of a positivity constraint. This looks very similar to positivity. So lambda x cube for x greater than or equal to 0, is it convex? X greater than or equal to 0, is it convex? Hmm. Yeah. Okay. Lambda, let's say, is positive. Let's not bother about lambda. This is convex. So what would it be? Let's write down. We don't have to look at component wise, just one scalar. What would it be? Sorry? We'll find a derivative, but what if this z is, say, negative? Yeah. Don't you need cases here? If z is negative, it will be 0. So why don't you work it out? If z is negative, So one simple trick is just try in your rough nodes, right? Try and set the gradient to 0, assuming that no x is greater than 0. This is a convex function, right? So d by dx equals 0 implies this rough nodes. Right? So sorry, this is yes. What R bridge, right? Two x minus z plus.
Yeah.
So the sufficient condition. What will be the solution to this? B square minus 4ac square, right? You just apply. What is b square here? Sorry. I'm saying if you set it to 0, what happens? And yeah, assuming that x is greater than 0. Huh? 24. Where is lambda? Where is lambda? Yeah, yeah. Okay. But there'll be a but there'll be a lambda here also, right? Wait. Did we miss out on something? 24 lambda will be here. Z lambda. Right. Divided by. Okay. So now you can just check if it's greater than 0. Under what conditions will it be greater than 0? Greater than or equal to 0? Huh? Any z positive? So if z positive, so yeah, you can now. So in retrospect, okay, let me just write down here. In retrospect, we are saying that so x is 4 or whatever. If z is greater than or equal to 0, and otherwise x is equal to 0. Right? Okay, so likewise, you could try and write down the expressions of the other cases. So the good idea is that you could identify some of these simpler cases, and now we'll very soon talk about the algebra, compose it for the more complex cases. This is just some examples. I would say try out these as homework. These are very simple. Okay. And I mean, we already seen this L1 norm. I'm just bringing it back in perspective. When C is non-differentiable, or recapping lasso, all we are trying to do, trying to bring out here is how exactly did we able to come up with the expression. It was based on the subgradient optimality conditions. So this is like a recap. Yeah, this is just a recap. Since we spent some effort, so this is again. I mean, I'll be skipping these slides. But let's now come to the all recap. I'll skip this. So now come to the table of proximal operators, where you look at lasso as one example, but we saw a couple of others, lambda x cube. Right. Maybe how was ours different? Lambda x cube, there's a mistake here, right? Well, lambda. Oh, I didn't have a half. I didn't have a half there. Okay. That's fine. This is fine. This is with a half. Minus lambda log x, you can come up with this expression. Z plus square root z square plus 4 lambda divided by 2. So by the way, these are all CXs. All what we see on the left hand side are examples of CXs. Okay. Now the lambda x cube minus log x are not necessarily of the constraint type. I mean, they are actual valid functions. Constraint indicator functions are typically 0 or minus 0 or infinity. So these still qualify as proper functions, not just the indicator type which we see for projected gradient descent. The last one, lambda x. Now here, it's lambda x is only defined to be non-trivial or rather non-infinity between the closed interval 0 alpha. So in which case, again, let's just look at the intuition behind these expressions, right? Without getting lost in the derivation. We have already derived this one. But let's look at the intuition for the other. Let's start with the last one. What's the intuition for the last one? You have a min of a max of z minus lambda and 0. How do you justify that? So if z is exceeding a particular value, you would like, or z minus lambda and 0, their max is exceeding a particular value, you're saying I would like to go with alpha. I'd like to hear your intuition. You don't want this overall term to exceed alpha, right? But what if that smaller component becomes less than 0? Is it possible? That will also not exceed 0. I'm sorry, it will not become less than 0. Right? So this is guaranteed to be greater than or equal to 0, and the overall expression is guaranteed to be less than or equal to alpha. That's what you're trying to do here. Simple. That's it. Sorry? So z minus lambda, the spirit is the same as in subgradient, sufficient condition using subgradient set to 0. It's like in ISTA, you were trying to trim values that were becoming large. Trimming is through the lambda. So in some sense, lambda acts as a regularizer. I mean, it's a different kind of regularizer, like a regularizer that's operational only between 0 and alpha. Okay. What about the others? The first one is the simplest of all. It's kind of simplified lasso. All you're doing here is you're basically looking at Z plus. It's not Z plus, it's like A plus. Give it a different, and Z is already inside. So A plus times sine of Z. This part is A. Okay. I hope this is all clear. We can probably proceed. Okay, so the more general set of functions for constant C, the prox is just Z. Well, C is basically ineffective, right? Affine functions A transpose X plus B is just Z minus A. Now, if you start putting thresholds, affine of A transpose X plus B when X is in some interval, then suddenly you'll find that you will need operators on Z minus A, like we had earlier. You see the relation. The affine function, like lambda X, was bringing in this factor lambda, exactly like here, right? Z minus A. A is like the lambda. So that, let me just type. I don't have space. Or instead of calling it constraints, I can say, well, post-processing operations. That may be more appropriate. Okay, that's the basic idea. Okay, so likewise for convex quadratic, it's A plus I, the whole inverse, Z minus B. So Z minus B is again figured here. It's the same. You had the Z, and if C was just B, is Z minus. Sorry, C was A transpose X plus B is Z minus A. If now instead we had B here, the Z minus B, and the quadratic component leads to preconditioning. This is called preconditioning. Okay. Okay, so now we go to the more generic calculus for the proximal operator. So all this is simple examples. But as I said, we can try and compose. Okay, let's spend a little bit more time on this part. By the way, this is book available from Amir Beg. Some chapters are online, and you'll find the derivations in that chapter 6. Okay, so let's look at these more generic settings. If you have sum of components, not just one CI but multiple CIs, but the CIs are such that they operate on individual components of the vector X. This translates into a product over components. Sum translates into product. Product over the proximal operator transformation. If you have linear transformation on X, lambda X plus A. Okay, so then what happens is the lambda starts reflecting here in the prox argument, prox of lambda square C. The C is a function, a prox additional function. You'll have lambda square here, operated on the lambda times Z plus A minus A. Right? So lambda. So this by the way, this is what you're doing, subjecting proximal to. So minus A is sitting outside. So you're doing a proximal step and then discounting for that additive term A. If you have 1 upon lambda X, then the third setting, you just have a division by lambda all through. Yeah, now if you have a Cx plus a quadratic component, right? So the Cx, I mean, that's why it's calculus. Cx could be any of these, right? The previous guys. And now to that, you're adding a quadratic component. So that leads to separate the subtraction. This is we have seen this again in the past. Any term involved with the linear component A gets subtracted from Z, and the gamma is just going to be sitting in the denominator. Actually, there should have been beta, and that beta you can see here. The effect of, so remember I talked about this preconditioning, but since we are dealing with a scalar, all this is in real, right? I mean, scalar. This beta is basically, it's not a matrix. If beta were a matrix, you would have an inverse pre-multiplication. So this is basically preconditioning, which we saw earlier. Right. So here only difference is that here we have, instead of a matrix A, you have A as beta or beta by 2 times an identity matrix. Okay. So if you have AX instead, AX plus B, that's what we saw here. So then, yeah, things get slightly more complex. You'll have A transpose post proximal operation. The last one is very interesting. If you have C of norm of X, if you have a non-differentiable function defined not on X but on norm of X. So you can do the prox and then look at the direction of that Z vector. So Z divided by norm of Z is a direction. Yeah, I mean, you can apply this. They are very handy, but we'll probably not spend more time unless you really want me to. I mean, it just looks. These look like they have fallen from the sky somewhere, but they have some rationale, which is what I'm trying to impress upon you. So especially if you can just take away. The take home message is that if you have a linear component, then you would subtract that, like the scalar associated with the linear component. If you have a matrix, then you'd have something like pre-multiplication, preconditioning, and so on. Okay, so this is the overall summary. And proximal gradient descent becomes gradient descent if that h, the second h, or we call it c, right? It becomes 0. Okay, if f is 0, one can minimize the non-differentiable function range. That's called the proximal point algorithm. The key, as we saw, is the computation of the proximal operator, and thankfully, in several cases, we are able to compute. And it's basically now well-established art. You can just apply. What if prox can be what if prox can be efficiently computed only approximately, right? So there are papers where prox is approximately computed, but one can still derive the convergence rates. So let's say I computed approximately using subgradient descent. So there are some analysis that have dealt with it, but it's still a very open area. Now, accelerated proximal gradient descent is similar to gradient descent. One can accelerate gradient descent to get convergence rates. Okay, so so this is going back to the overall gradient descent scheme or subgradient descent comparison. But my point is now we can also apply acceleration to get z. Can apply acceleration to get z, and actually convergence rates improve. So that's accelerated generalized gradient descent. So it's not just accelerated, but accelerated generalized gradient descent. I'm not going to delve into it because the logic is exactly the same as I said. The only difference is z has to be computed using the accelerated step. And somewhat relevant to your assignment too. We are just going to release it now. So you can see that if you do Nestor accelerated over generalization, again you'll find a big difference as against subgradient method. So subgradient is the worst of the lot, right? But you could have applied generalized gradient descent, which has given you a big gain from the subgradient. But any advancements you probably have in the momentum space, right, can benefit the generalized gradient descent. That's what I'm trying to impress upon you. That's why it's a very, very neat generalization of gradient descent. And what I'll do in the these are some extra and optional detailed slides on accelerated generalized gradient descent. Yeah, I know that. I just thanks. So I'll just leave you with these extra slides. I'll not go into these. These are things just get very, very messy with too many more notations and updates. So I have to use unprojected or non-proximal updates, and then you have to bring the proximal part. So the analysis is very, very messy, right? But I provide some proof of its rate of convergence, etc., which you're welcome to. I try to color code it in case you're interested. Okay, what I'll do is the next class I'll be concluding one last part, which is the projected gradient descent. Because just like I said, there are some rules for proximal. There are some interesting tables for projected as well. These are very handy. So just to give you an idea, right? In the idea in projection is that if you have this constraint space, I'm going to project at the end of or through the proximal step. At every step, I'm going to just project back. And it turns out that there are some very neat forms here, like very nice projection operations as well. And there's in fact a calculus of projections as well. Okay. So I'll just conclude this part, and then we will. I'll also motivate how this is obtained. All this is obtained through a use of Karsh-Puntakar optimality conditions as necessary and sufficient in certain cases. So I will not go over the details of how they're obtained because I want to move to the next part, which is discrete optimization. I'll be leaving you with some optional lectures which you can go through if you want. But I'll very briefly talk about the KKT conditions themselves. What are those KKT conditions which were used to derive the projection operation? So that's the agenda for, and then we'll move on to right. Yeah, it's actually prox, but prox with an indicator function. You can call it projection if you want, but it's the same as prox with an indicator function. That's fine. Okay, so yeah, I'll leave you on this. We'll probably we'll hopefully complete this in the first half of next class and then move on to discrete optimization. Thanks.